के बी मिश्रा कनेक्ट तो हो गया है। So, respected speakers and dear participants, welcome to the third technical session of International Conference on Futuristic Materials. In this technical session, we have one plenary talk by Professor K.B. Mishra from Czech Republic, followed by 3 invited talks. To chair this session, I would like to invite Professor Dinesh Yadav sir, and co-chair will be Dr. S.A. Khan from Physics Department of St. Andrews College, Gorakhpur. Dr. S.A. Khan, sir, can you hear us?
Yes, yes.
Please conduct this session since Dr. Yadav is taking some time to join this session.
Okay, okay. अरे यार just 1 minute. सर जल्दी आओ तो मम्मी का मोबाइल लाओ तो जल्दी से मम्मी का मोबाइल लाओ
So due to some technical problem, I would request Professor S.N. Tiwari, the Dean Faculty of Science, to introduce our chief speaker of this session, Professor K.B. Mishra. Professor Tiwari, sir.
Thank you, Dr. Ambrish, for inviting me. The chairman of this session is Professor Dinesh Yadav, former head of the Department of Biotechnology and a senior professor of the Faculty of Science. Before he joins, I would like to start the session with a small introduction to the plenary speaker of this session. Dr. Kumudband Mishra is a student of this place. He got first division in MSc and first division in BSc and MSc, both from the DDU Gorakhpur University. He belongs to a very small village from where he came to this university. Afterwards, he joined Allahabad University for completing his Doctor of Philosophy degree. And he did his work using laser source, particularly on biological systems. Later on, he became associated with many projects, ISRO projects, and at M.N. Saha Center at Allahabad University. And then he moved abroad and he did tremendous work of interdisciplinary nature, and he has very good publications to his credit. He is a recipient of Young Scientist Award by the International Academy of Physical Sciences. And besides his heavy involvement in multinational project, he has demonstrated the important use of chlorophyll fluorescence imaging techniques for monitoring drought and cold stress tolerance in plants. His expertise on the use of biophysical methods for probing abiotic stress-induced tolerance mechanisms in Arabidopsis thaliana and his work on relevant crop plants has made his research work interdisciplinary and relevant. Further, he has also been invited to join an Antarctic research project at Maastricht University, Czech Republic, and took initiative on integrated application of various non-invasive methods. For example, chlorophyll, efflorescence, reflectance, and Raman spectroscopy on Antarctic lichens that may be highly useful to understand the evolutionary role of symbiotic organisms. Dr. Mishra has been a member of the management committee representing the Czech Republic in 2 European coast action projects. He developed several research techniques and research collaborations and is a co-author of several joint publications. With these words, I am happy to invite Dr. Kumudband Mishra to deliver his plenary lecture, and I also acknowledge and thank him for accepting our invitation to be a part of this international conference. With these words, I invite Dr. Kumudband Mishra to please deliver his talk. Dr. Kumud. Hello.
Hello, am I audible?
Yes, you
Yeah.
continue.
And do you able to see my presentation?
But you go to full screen.
All right, all right. So thank you, sir, for inviting me and giving me a nice introduction. Uh, Let me see if is it okay. Is it full screen now?
Now it is okay. You can continue now.
Yeah, thank you. Thank you and
Dr.
greeting to
Kumud,
all. Yes, sir.
Dr. Kumud, are you all right
Yes,
health-wise?
yes, yes. I'm very well.
Okay. So you are allotted 30 minutes time and try to stick to the time.
All right, all right. So thank you for a nice introduction. Uh, uh, and I'm going to talk about as sir told that I did my BSc and then MSc from Gorakhpur and then shifted to Allahabad and further I migrated to Czech Republic as a visiting scientist and then I continue work here. Currently I'm going to talk mainly about the methods that we use, like spectroscopic method that we use in our research. And basically the work that we did with Antarctica projects. Um, a little bit, I would like to give introduction of my institute. So we are from Czech Globe, that is Global Change Research Institute of Czech Republic. This is situated in Brno, that is economic city of the Czech Republic. Well, this is very small country, you know, with 1 crore, 5 lakhs people. But still 500,000 and 5 lakhs people are infected by corona. We basically our institute work for biosphere, atmosphere, ecosystem, and society, you know, to have a better future. So we work in all dimensions. We have several institutes around Czech Republic, but apart from this, we collaborate with almost all European countries and USA. Um, we have lots of infrastructure. For example, we have our own aeroplane, you know, to monitor the terrestrial ecosystem. We have a very big tower. I think this is one of the largest in Europe, to see the atmospheric effect of different atmospheric gases. We have lots of other instrumentation like you can see in the picture, where we do lots of experiments. We also work uh, in the crop plants. We work in laboratory to understand the molecular level of the plant systems. So we have 6 domains in our institute and 17 research team, and we have many cooperation with spin-off companies. So main optical signals that we work on to understand switch on and off of photosynthesis, and to understand the regulation of carotenoids. We use reflectance signal of chlorophyll fluorescence, and we recently we used Raman scattering uh, to monitor the life of lichens. Uh, this is some basics, like you see here the different irradiance and pigment absorption line. So the upper one is top of the atmosphere, like above atmosphere. This is the irradiance in blue line, you see, and then on the ground you see the red line is the irradiance label, and you can see there is a differences For example, there are oxygen bands here, and there is a absorption in the light due to oxygen and hydrogen banded. So basically, they are Fraunhofer lines that again another part of our institute, we use it to monitor the light-induced fluorescence even from the satellite. It is possible to do this, and European agency is soon going to launch satellite to monitor the fluorescence from space. And then you see there are lots of absorption line. They are from chlorophyll A, chlorophyll B, and different carotenoids and another pigments. So basically, we use we use this absorption line to understand the pigments inside the plants, inside the leaf, or inside the lichens. And we use spectroscopic signal to understand not only photosynthetic mechanism, but also its impact on different photochemical mechanisms. Uh, Photosynthesis is very complex process. Uh, it has antenna pigments that absorb light and transfer it to series of photochemical reactions starting from femtosecond to second day, and then label. So basically, these photochemical reactions form uh, uh, ATP, NADPH by light reactions, and these ATP and NADPH are further used in carbon reactions, where uh, mixing with CO2 they form carbohydrates, and they form hydrates, and also that we use these carbohydrates and also oxygens, that is a byproduct of photosynthetic reactions. We use it in our day-to-day life. And basically, we so this is still very complex phenomena, and still it is not much known about this. Still many things are debated. uh, and we try to understand the photosynthesis by different non-invasive tools and methods. If we see a kind of how it works, so basically there is a light. When there is a light falls on leaves chloroplast, there is a scattering, there is a reflectance, and absorbed light is being used for photosynthesis. For dissipation of heat, part of this is dissipated, and then there is a chlorophyll fluorescence. Chlorophyll fluorescence is just 2 to 3% of the absorbed light, but still it is very informative. Apart from chlorophyll fluorescence is very dynamic, but upper part of the leaves, they emit blue-green fluorescence that we can also measure. And part of light is transmitted, and it follows energy conservation theory, like reflectance, transmittance, and absorption is equal to constant. uh, we use reflectance signals in our research a lot. There are some examples here, like you see how it works. Like this is from visible region from 400 and 400 nanometer to 2500 nanometer, and you see the reflectance of a green vegetations, and then there is a this is the reflectance of a dry vegetation. So you see there's a big changes in between them. So there are different bands apart from chlorophyll. There are water absorption band, and there are also bands that can reflect biochemistry at different level of canopy. In the lower part, you can see there are, for example, if we measure the reflectance from a leaf uh, plants, and there are upper leaf and lower leaf, and they have big difference in the chlorophyll, and then you can see there is a red edge, so there is a big difference. So we use these differences to measure, to understand the photosynthesis and insight mechanism. Also reflectance line can measure. For example, if we in the morning we have a very low light, in the noon time we have very high light, and the plants changes, some of the pigments, carotenoids like zeaxanthin to vioxanthin, from low light to high light, uh, uh, to protect the photo system. And reflectance, by measuring reflectance signal, it is possible to measure these changes. Also we can use different kind of reflectance, like reflectance. There are 3 wavelength dependent indices that we can use to identify the uh, the the exact pigments. For example, chlorophyll A, chlorophyll B, and different kind of carotenoids, anthocyanin. It is possible to use reflectance phenomena to identify these pigments. So basically, now I'll talk about some chlorophyll fluorescence. Chlorophyll fluorescence was discovered in 1931 by a German scientist, Kautsky, and we also call it Kautsky kinetics. You can see here, when we use UV light, you can see how chlorophyll fluorescence looks like, and in dynamics, in millisecond order in the right side, and in second scale in the left side. You can see how we can monitor the yield of fluorescence. And now we have, with the development of technology, we have lots of instruments, even handheld instruments, that can be used to measure the fluorescence yield. Here I would like to show you some spectra, like uh, fluorescence spectra at room temperature and at liquid nitrogen temperature. So basically there is a 2 fluorescence band, PS2 and PS1. This is called PS2. Second band is far red band. This is also from PS2 plus PS1. But when we put the samples at liquid nitrogen, you can see it is possible to identify some other bands, uh, and that is correlated to some different protein complexes like CP43 and CP47. But you see there is a very high increase in the PS1 band. So basically the contribution of PS1 and PS2 are different, and at low temperature, contribution of PS1 is high. So we use these tools. We try to understand the mechanism of plants, and this is one example where we use fluorescence kinetics and fluorescence spectra to understand the low temperature induced modulation in photosynthetic reactions. Uh, uh, so basically this work was initiated, was done by me along with collaborators from Germany and Govindji from USA. Then I would like to show another example where different inhibitors can have different effect on photosynthetic reaction, and we can exactly monitor these things. For example, we put DCMU in the leaves, and DCMU can block electron flow in the photochemical reactions. And you can see when we insert DCMU, you can see there is no dynamics of chlorophyll fluorescence transients. This is much more clear in log scale below. And methyl viologene, this is another inhibitors. Well, that it is speed up the photochemical reactions, and you can see there is a very low intensity, and we can monitor it. Then there is a nigericine. Nigericine is another antibiotic that can dissipate the energy created inside the thylakoid membrane, and we can see its impact. So by using these inhibitors, we were able to monitor how reaction basically works, and how we can specifically understand the mechanism by using simple inhibitors. And we use these information to understand the switch on and switch off of photosynthesis in lichens. I think I don't need to give introduction to Raman spectroscopy. It is Rayleigh scattering, Stokes Raman scattering, and anti-Stokes Raman scattering. And this is again very difficult to monitor the signal, but nowadays even handheld instruments are available to monitor the Raman signals, and we use this information to in our research to understand the regulation of carotenoids. So this is some simple spectra of Raman spectra of carotenoids. We use 514 laser line to get the Raman signals, and then we found carotenoid structures, carotenoids spectra. It gives spectra of whole carotenoids. It is very difficult to identify the individual carotenoids, because there are many carotenoids in the plant leaves. So now I will talk about our Antarctica research. So Antarctica is the coldest place on the earth. It has average winter time. It has only 2 seasons, summer and winter. And the highest temperature yet recorded is 15 degrees centigrade, and lowest is around minus 90 degrees centigrade. And you can imagine the life in Antarctica, and but still there are some life in Antarctica in the form of lichens. Lichens are symbiotic organisms. They along with fungi and photobionts. Photobionts can be algae or cyanobacteria. They form life, and they contribute to the carbon cycle of ecosystem of Antarctica. Our team, we have a group that visit every years in Antarctica, and they brought lichens that we use in our research. So basically in this article that I show you, we use reflectance signal in the left side, and you can see the dry lichens, that is at 5 degrees centigrade. It has no signal at all. But when we hydrated it with water, simple water, we can see the variations in reflectance signals after 48 hours of hydration. You can see in the middle there is a pictures of a dry state, and after 48 hours of hydration, how it looks like. And there is a chlorophyll fluorescence images of different parameters that shows heterogeneity in its heterogeneity of heterogeneity and existence of photobionts inside the lichens, these little lichens. We use this techniques like we use Raman spectra and Raman shift of Raman band to monitor the carotenoid. So basically, if there is a shift, it can be shift because of synthesis of carotenoids. If there is no shift, we assume that it has constant carotenoids. So basically, we observed that after hydration of 48 hours, there is a shift in these bands, Also, this is clear from the images. And the brown area of the lichens after hydration, and the green area, they have different kind of shifting. And by using these information, we can identify if there is a synthesis of de novo synthesis of carotenoids in lichens or not, and how the life in Antarctica takes place. Further, we use three different kind of lichens. For example, this is three lichens you can see here, and then upper surface, lower surface, and post hydration, how it looks like. So and then we perform our experiment to understand how photosynthesis switch on in this lichen by measuring chlorophyll fluorescence. So you can see in these three kind of lichens, after 4 hours of hydration, there is a signal, there is a dynamic of chlorophyll fluorescence in three lichens, and then we measure the yield of primary yield of photosynthesis, heat dissipation, non-photochemical quenching. Again, there is a regulatory part of it and non-regulatory part of it, and we found there is a diversity in these lichens, photosynthetic pigments. Then we use like seconds. This is we use like 1 second time
Excuse
resolution.
me, Professor Mishra.
Yes.
Since we are running out of time, so please try to conclude within 2 minutes. Please, sir.
All
And
right.
I would request Professor Dinesh Yadav, sir, to chair this session and conduct further.
Yeah, I'm here actually, and just
Okay, sir.
All right, thank you. So basically, by measuring different fluorescence, and by measuring T50, like half of the time that it takes, it take for from zero state to some photochemical state, we can measure the. We can know that it is very there is a very fast modulation of photosynthesis in minute time scale. There is a regulation of carotenoids, de novo synthesis of carotenoids, and we are again we are using again some other form of fluorescence to understand its non-photochemical quenching, like how it really works in highlight and in such an extreme environment. I don't need to go for conclusion, but I would like to thank my collaborators from different parts of the Europe and from Czech globe, Masaryk University, and I thanks to all of you, and I thank Professor Tiwari and Ambrish for inviting me for a talk, and I'm ready to take some questions if there is.
hello, am I audible?
Yes.
Thank you, Professor Mishra. It was a really very interesting talk. Actually, it is a different angle on photosynthesis, because we also work on little bit of photosynthesis. If anybody want to ask question, any person from the audience? Anyone interested to ask, because it was a really very interesting talk. So if not, then from the organizer and from my behalf, we would like to thank Professor Mishra for enlightening us on a very different aspect about the photosynthesis, and that too on which and the carotenoids in Antarctica lichens. Thank you very much, Professor Mishra.
You're welcome. Thank you.
Okay, then we will continue now. Now the next talk is by Dr. Siddiqui from Saudi Arabia, and he is going to talk on molecular modeling of organic PN junction diodes. I would like to invite him and deliver the talk, because we are running short of time. Dr. Siddiqui.
Yes, Thank you, Professor Yadav.
Yeah.
I'm highly thankful to the organizer of the conference, especially Professor S.N. Tiwari, Professor Yadav, and Dr. Amrish for giving a chance to present a piece of my work here. So, since the time is very limited, so I will try to conclude my talk as early as possible.
Yeah.
Could you see my screen?
Yeah, yes, okay.
Okay, so the title of the talk is Molecular Modeling of Organic PN Junction Diode. So first of all, the outline of my talk will be introduction, a brief introduction of organic electronics. Then I will talk about organic PN junction diode and the working of the organic PN junction diode. Then, since it is a purely computational work, so in next slide I will discuss about the computational method and simulation protocol. Then I will show you some results, and then finally I will conclude the talk. So organic electronics. Nowadays, since last 20 years, people are paying significant attention for the discovery of the organic semiconductors and for the possible use of these organic semiconductors in organic devices, various kind of organic devices like organic field effect transistors, organic molecular diodes, organic dye-sensitized solar cells, and organic logic gates, etc. So the reason for the interest in the organic semiconductor is that since they are environmentally friendly and they are cost effective, and the most important thing are that they are easily tunable. By changing the functional group, you can tune the properties of these organic semiconductors, you can tune the electronic properties, you can tune the optical properties. So this is the main reason for the interest in the discovery of organic semiconductors. So the performance of the semiconductors primarily depends on the charge transport. So it is of great importance to understand the theory of charge transport as well as the relationship of the charge relationship between the structure and the electronic properties, and the structure and between the structure and the optical properties. Charge transfer systems mainly composed of an electron donor moiety on one side and electron acceptor moiety on the other side constitute a subcategory of organic molecule that is known as the push-pull systems. So here, since the title of my talk is about organic PN junction diode, it is also known as the molecular diode. So first time the organic PN junction diode was proposed by Aviram and Ratner, and this was the basic model. They proposed that if we can join one electron acceptor moiety, they here used TC and Q molecule, with one electron donor moiety via a sigma bridge. So this should work as a molecular diode. It should show the characteristic similar to the silicon-based PN junction diode. So the diodes are the basic building block of many electronic equipment. They are used as a rectifier. These diodes are the building block of many three-terminal electronic devices like field effect transistor, like bipolar transistor, and the diodes have vast application in electronics. So diode is simply a two-terminal device and operates like a silicon-based PN junction diode with distinguishable electronic states, that is highly conductive means on state, and the less conductive, that means the off state. Now the working of these organic PN junction diode or the molecular diodes. So as I show you in the last slide, we place electron donating molecule on one end and electron withdrawing molecule on the other end. So the electron donating molecule with substantial electron density, that is known as the N-type organic molecule, and an electron withdrawing molecule with deficient electron density, that is known as the p-type molecule, are linked with a sigma bridge spacer. So it will conduct in one direction, similar to the silicon-based rectifiers. Due to the presence of electron donating molecule on one side, the energy levels will be raised. And on the other hand, due to the presence of the electron withdrawing molecule on the other side, the energy levels will be reduced. So due to this reason, a potential barrier that will be equal to the difference of the energy will be developed. So for current conduction to occur, electrons must vanquish the potential barrier from electron withdrawing molecule to electron donating molecule. And this is the fundamental principle, the fundamental aspect of for the working of the molecular diodes. So computational method, we modeled here two diodes. Both are the donor sigma acceptor type push-pull system, namely TCNQ. TCNQ is an electron acceptor molecule, sigma bridge, then P saxiphenyl. This is an electron donor. And the second diode was NTCDA. This is the short form of a molecule connected with, again, P saxiphenyl via sigma bridge. So here we change the electron acceptor molecule in the two diode, but electron donor molecule in the two diodes are the same. So here TCNQ and NTCDA molecules are well-known electron acceptor, and P saxiphenyl is well-known electron donor. These two molecular diodes were modeled using Gauss-View 4.3 version. And after the molecular modeling, we perform geometry optimization using Gaussian 09 program package. And the functional we choose here is B3lib, and the basis set is 631 GTP. That is nice for the optimization of ground state energy of organic molecules. Since every electronic device always work under a considerable electric field, so it is of great importance to optimize the molecular structure under an electric field. So in the first step, we optimize the molecular geometry of these two model diode without any electric field. Then we re-optimize the molecular geometry with different electric field in two directions. The first direction was from donor to acceptor molecule, and the next direction was the acceptor to donor molecule. In D to A direction, when we optimize the geometry, so we found that there is a sharp decrease in the homo-LUMO gap. And because of this reason, we choose a small increasing step just of 0.02 volt per angstrom. But in A to D direction, when we apply the electric field in this direction, we observe that the homo-LUMO gap is increasing with respect to the strength of the electric field. And here we apply the increasing step of 0.05 volt per angstrom. These are the two optimized structure of the molecular diode. The first molecular diode, this is a TCNQ, electron acceptor moiety. This is a sigma bridge. And this is P saxiphenyl, and electron donor. Here again, we change the electron acceptor moiety from TCNQ to NTCDA, and the sigma bridge and the electron donor moiety is the same. Now I will come to the results. So the first result is the electric field dependence of homo energy, LUMO energy, and homo-LUMO gap for these two model diodes. In the first figure, figure A, if you can look on the x-axis is electric field in volt per angstrom, and on the y-axis homo energy, LUMO energy, and the HLG means homo-LUMO gap, all in electron volt. So when the electric field was 0 at this point, you can look that the homo-LUMO gap is around 1 electron volt. And in the second molecule, when the electric field was 0, that means without electric field, the HOMO-LUMO gap was around 2 electron volt. But when we increase the electric field in D2A direction, this is the positive, I show you this with positive sign and negative sign. So in D2A direction, from donor to acceptor direction, when we increase the electric field strength, we found that sharp reduction in HOMO-LUMO gap. The HOMO-LUMO gap without any electric field was about 1 electron volt. That was also a moderate HOMO-LUMO gap as far as the charge transfer is concerned. But when we increase the electric field in this direction, we saw a sudden decrease in HOMO-LUMO gap. In second molecule, the HOMO-LUMO gap without any electric field was around 2 electron volt. But when we increase the electric field, we again saw a sudden reduction in HOMO-LUMO gap. On the other hand, when we increase the electric field in the opposite direction, that means from A to D direction, acceptor to donor direction, we saw that HOMO-LUMO gap increased in the first case also and in the second case also. But after one threshold value of the electric field, we observed some surprising result that after this point, HOMO-LUMO gap start decreasing in the first molecule and in the second molecule also. So we can conclude that in this direction, when we applied electric field in D2A direction, HOMO-LUMO gap shrinks. That means the charge transport between the donor and acceptor moiety is highly probable. When we apply the electric field in the opposite direction, we can call it reverse direction, HOMO-LUMO gap increases, and after a threshold value of electric field, it start decreasing. We can resemble this decrease in the HOMO-LUMO gap in both molecules with the breakdown voltage of the diodes. Next, to confirm our results of the HOMO-LUMO variation with respect to the electric field, we calculate the NBO charges, the natural charges on the donor moiety, bridge, and the acceptor moiety under various electric fields. So on the x-axis, you can see electric field. On the y-axis, charge on donor, charge on bridge, and the charge on acceptor. So you can see here, at 0 electric field, there was very nominal charge near about 0 on the donor. But when we increase the electric field strength in D2A direction, we saw that the positive charge on the donor is increasing. That shows the electron transfer. Here again, we got the same type of variation. When we increase the electric field strength in D2A direction, we saw the increase in the charge on the donor. However, the charge on the acceptor, we can see here, when we increase the electric field, the charge on the acceptor was negative, and this negative charge again decreases. So the variation of the NBO charge supports the variation in the HOMO-LUMO gap. Next, we calculate the electric dipole moment with respect to the 1 minute. Again, on the reverse direction of the electric field, on the opposite direction of the field, you can again see that the charge on the donor is decreasing and the charge on the acceptor is increasing. Here again, the same type of variation. If you can compare this with the variation of HOMO-LUMO, so you can easily identify that both graph, like this is the variation of the HOMO-LUMO gap with respect to the electric field, both are complementing each other. Next, we calculate electric dipole moment again with the same interval of the electric field in both direction, and in D2A direction, we observe that electric dipole moment significantly increases for both the molecule. While in reverse direction, that means A to D direction, the electric dipole moment suddenly decreases in both cases. But After a threshold value of electric field in reverse direction, we again saw an increase in the electric dipole moment. This increase again resembles with the variation of the HOMO-LUMO gap with excessively high electric field in the A to D direction or reverse direction. So it again indicates something like breakdown in the diode. So now I will conclude my talk. So this in silico study, that means the computational study of two donor bridge acceptor molecule systems, strongly suggests that these moieties are the excellent charge transfer materials. The HOMO-LUMO gap of the first model diode and the second model diode was 1.03 electron volt and 1.94 electron volt. And this moderate HOMO-LUMO gap further shrinks when we applied the electric field in D to A direction. However, when the electric field direction was reversed, the HOMO-LUMO gap increases with a certain threshold value of the applied electric field. When the electric field goes beyond that threshold, the HOMO-LUMO gap again decreases. And the variation of the HOMO energy, LUMO energy, and HOMO-LUMO gap with respect to the applied electric field is found in accordance with the variation of the electric dipole moment as well as with the variation in the NBO charges on donor bridge and acceptor moieties. So the present investigation clearly suggests that the current conduction is highly probable in one direction. Furthermore, after a threshold value of applied electric field in the opposite direction or reverse direction, reverse current flow is also highly conceivable. So this behavior strongly suggests that these modeled donor sigma acceptor moieties or these push-pull system might be the excellent contenders for molecular diodes. So thank you very much. If you have any questions.
Yeah, thank you, Dr. Siddiqui. If there is any question from the audience, definitely we will look for it. But if there's no question, meanwhile, because you have in time, I will just like to inform to the audience that Dr. Siddiqui is a product of University of Lucknow. He did his PhD from Lucknow in 2009 and postdoc from Indian Institute of Science. After that, he joined Nazran University, Saudi Arabia in 2011 as assistant professor, and later he was promoted to associate professor in March 2017. And to his credit, he has got more than 50 research articles that too in a very peer-reviewed journals. So just an introduction to the audience about Dr. Siddiqui. I think there's no question. So definitely we would like to thank Dr. Siddiqui from the organizer, from the all organizer, that it was a very good lecture for the audience. Thank you very much, Dr. Siddiqui.
Thank you very much, Professor Yadav. Thank you very much.
Okay. Next lecture is Dr. Anar Singh from Lucknow University, and he is going to talk on induced interfacial magnetization in a very complex heterostructure, BiFe-03, La2, SR1, MnO3. So Dr. Singh, I think you should start the lecture, and definitely if time permits, I would introduce to the audience, Dr. Singh.
Thank you, sir. First, I would like to thank the organizer of this event for giving me opportunity to talk about my work here. The title of my presentation is Induced Interfacial Magnetization in a Multiferroic and BiFe-03 and a ferromagnetic LS-MnO3 heterostructures. This is the outline of my talk. First, I will talk about magnetoelectric multiferroic materials, and then little bit a brief introduction to bismuth ferrite, and then I will highlight the important properties, multiferroic properties of bismuth ferrite, and then we will discuss about the heterostructures and its results, and then I will conclude my talk. So multiferroic materials are defined as the single phase materials with simultaneous magnetic and ferroelectric orders are termed as multiferroic materials. And if there is a coupling between these two orderings in such a way that if we can tune electric polarization by magnetic field and magnetization by an electric field. This phenomena is known as magnetoelectric effect, and such materials are termed as magnetoelectric multiferroics. So magnetoelectric effect can be linear or of higher order. Linear magnetoelectric effects, polarization linearly depends on the magnetic field, or magnetization linearly depends on electric field. And this type linear magnetoelectric effect is basically strong, and the higher order coupling in which uh, polarization varies with h square, h cube like terms, and they are generally weak. These materials are very they are they have potential for technological applications like high density data storage, low power memory and logic devices, and other spintronic devices. So, and bismuth ferrite is one of the most investigated multiferroic material, because it is there are very few multiferroic materials known this time, and bismuth ferrite is one of them, and its ferroelectric and magnetic ordering temperature not only much above the room temperature, but these two orderings are also coupled to each other, and it shows very high ferroelectric polarization. So these properties of bismuth ferrite raise the possibility of potential devices based on magnetoelectric coupling, which can be operated at room temperature. So this is the schematic view of the structure of bismuth ferrite, in which this is basically a perovskite structure, in which the cations and anions move with respect to each other along the 111 pseudo-cubic axis, and the two consecutive octahedra along 111 axis rotate in anti-clockwise opposite to each other about this axis, and this structure belongs to rhombohedral structure in R3C space group with A minus A minus A minus tilt system, and these are the shift of cations in bismuth ferrite structure, and this is the tilt angle. Despite of strong large shift of cations, the ferroelectric polarization observed in bismuth ferrite was very low, nearly 6 microcoulomb centimeter uh, square, and this low value of ferroelectric polarization is because of the high leakage current problem in bismuth ferrite, because Fe can have +2 or +3 states, so there is a exchange of electron, and that reduce its ferroelectric polarization. But later some thin films, insulating thin films, were grown and single crystal, in which large ferroelectric polarization close to 100 microcoulomb per centimeter square were observed. And this is the magnetic structure of bismuth ferrite, in which the magnetic moment of iron, which is the only magnetic ion here, the magnetic moment of iron are ferromagnetic coupled in 111 pseudo-cubic direction, and they are anti-ferromagnetic coupled between adjacent 111 planes. So basically in bismuth ferrite, Fe spins construct a G-type anti-ferromagnetic ordering. So here a G-type anti-ferromagnetic ordering is shown, and which is in which the Fe spins are also incommensurately modulated with a periodicity of 620 angstrom. So in addition to G-type antiferromagnetic structure, there is also a cycloidal spin structure which has a periodicity of 620 angstrom. And we can see that for every plus spin, there is a minus spin. So net magnetization over this scale is 0. So if magnetization is 0, then in this case, we don't have linear magnetoelectric effect. We can, in bismuth ferrite, we can have only higher magnetoelectric effect. So that's why the magnetoelectric coupling in bismuth ferrite is weak. So in order to improve the magnetoelectric coupling, we need to suppress this spiral spin structure so that we can have non-zero magnetization and we can get linear magnetoelectric effect. So these are the possible ways by which we can suppress the spiral spin structure. So see here, this is MH curve for bulk bismuth ferrite, and we can see that there is no macroscopic magnetization, no ferromagnetic component. But in case of epitaxial strain thin films, we have some ferromagnetic component, which is close to 0.0, is less than 0.1 mu b per Fe. And in case of nanoparticles of bismuth ferrite, for example, if we reduce the size of the particle below the periodicity of the spiral spin structure, which is 62 nanometer. So for nanoparticles having size less than 62 nanometers, we have some ferromagnetic component. So this is another way of melting spiral spin structure. And the third route is to make solid solutions of bismuth ferrite with other perovskite materials, or by some kind doping at A or B site of the perovskite structure. So we can also have here some ferromagnetic component. But in all cases, we have magnetization. The ferromagnetic component is less than 0.1 mu b per Fe. And this is very small. And such a small magnetic moment cannot be controlled by electric voltage. So this is the challenge which we are facing to make device of bismuth ferrite. So what people are doing nowadays, they are trying to combine the bismuth ferrite with some ferromagnetic materials. So there are some composites have been investigated, like composite of bismuth ferrite and CoFe2O4. This is a ferromagnetic. But again, we have another challenge in such composites, are we lose the ferroelectric polarization of bismuth ferrite because of the conductivity, because bismuth ferrite has already some leakage current problem, and if we make composite with ferromagnetic materials which are also conducting, so we lose the electric polarization of bismuth ferrite, and hence we also lose the coupling phenomena. So what we have tried, that we have prepared heterostructures of bismuth ferrite with a room temperature ferromagnetic material, that is LSMO. This is also a perovskite structure, and the ferroelectric TC of this LSMO is 370 K, which is above the room temperatures. So the advantage of, because we are trying to get the ferromagnetic component and magnetoelectric effect at room temperature, so that device can be made. So what is idea behind making this heterostructure is that, so here because in bismuth ferrite, if we, by applying electric field, if we change the polarization from one plane to another plane, the spin rotation plane also changes. So by modifying the spin rotation plane of bismuth ferrite, we can also change the magnetic property of the whole system by interface effect between the magnetic ions like Fe and Mn. So we have grown BFO LSMO heterostructure using pulse laser deposition technique. This is the XRD pattern of the heterostructure. The strongest peak corresponds to substrate, which is SRTiO3, on which the films were deposited. And the peak on the right hand side to the strongest peak is the peak of LSMO. And this at lower 2 theta, the lower L value, this peak marked with star corresponds to the bismuth ferrite 002 type reflection. And the films were deposited at various temperature in different oxygen pressure. And we can see here that with decreasing the deposition temperature, there is a change in X-ray diffraction pattern. Means some new peaks appear at lower L values, and finally at 570 degrees centigrade, we have a
Yeah, Dr.
peak.
Singh, I would like to tell that we are running short of time actually.
Okay, okay,
Yeah,
just
yeah, sure.
okay. Thank you. So I will try to summarize quickly. So we have uh, done reciprocal space mapping to analyze the crystal structure of these films using X-ray diffraction pattern and from this analysis, we have observed that basically our bismuth ferrite from monoclinic structure transformed to a tetragonal phase with very large C/A ratio. So by changing the deposition condition, we can transform the monoclinic phase of bismuth ferrite to a tetragonal phase, which has a very strong polarization. And from AFM studies, we can see that the growth model has changed if we reduce the deposition temperature, and there is a kind of island growth, and a local strain is introduced because of this change in growth model, and this strain is basically responsible for the structural phase transition. And we have also investigated the magnetic properties of these cis heterostructures, and we find that the ferromagnetic component of heterostructure is significantly larger than the ferromagnetic component of the ferromagnetic layer, LSMO. So this shows that in heterostructure, magnetic properties is enhanced significantly, and this component, the enhanced component, is coming from the bismuth ferrite layer, because LSMO is already ferromagnetic. So we have significantly increased the magnetic property of the bismuth ferrite by depositing that film on a ferromagnetic layer. And this enhancement is coming because of the coupling between double ferromagnetic coupling between the Mn and Fe ion near the interface. So this system, this heterostructure could be a material to make some device based on the magnetoelectric effect. So this is the conclusion of my talk, where I just want to highlight that the ferromagnetic component of bismuth ferrite has been increased significantly by depositing this multiferric compound on a ferromagnetic layer. I would like to acknowledge our collaborators from National University of Singapore. Thank you.
Thank you, Dr. Singh. And if anyone want to ask question, I think most of the people, they are asking question in chat only. But just for the audience, I would just like to inform that Dr. Anar Singh has got a very impressive biodata. He has done MSc, PhD from BHU. Then he got postdoc experience in Switzerland and National University of Singapore. Then he got a prestigious Inspire Faculty Award, where he joined in Institute of Chemical Technology, Mumbai. And later on, in June 2016, he joined University of Lucknow as assistant professor. And from there onward, he is doing a lot of work, and he's got a lot of publication also. And really sorry, Dr. Singh, that we could not extend because of the time constraint. So from the organizer point of view and from all of us, thank you, Dr. Singh, for a very good lecture.
Welcome, sir. Thank you. Thank you so much.
Now, the last lecture in this technical session, I would like to invite Dr. Dev K. Mahato, NIT Patna, Bihar. So he is going to talk on electrical properties of complex perovskites for future application. So Dr. Mahato.
Yes, I am here.
Okay. Then hello. You can, yeah, definitely. Then you can start. Dr. Mehta, you can share your PPT.
Yes, yes, I am trying, sir. I am trying.
Okay.
Dr. Mahato, please unmute yourself. I think there is some problem from Mahato's side. So
Yeah. So what we should do? We should continue or we should end?
he's trying to reconnect, sir.
Okay. That's
Sir, you are not audible. We can't hear you, sir. Actually, your mic is not properly connected, as I think. Yes. So now please unmute yourself. Okay. Now start share screen. May I help you, sir?
Okay, I am trying.
May I
Okay,
help you,
so,
Soumitra?
yes, please help me.
Please open your PowerPoint on your desktop first.
Yes, I have opened.
Actually, sir, are you connected with mobile phone?
No, in laptop.
Okay. So once you have opened your PowerPoint slide, then please go to share screen. Yes, we can see your screen.
Oh, okay. My PPT is visible. Hello?
Actually, sir, you have opened. Are you connected with online website through?
Yes.
Oh, so I think there may be some problem in sharing the screen.
Babu, come. देखिए तो शेयरिंग नहीं हो रहा है जल्दी देखो देखो शेयर नहीं हो रहा है
यार इसके ऊपर क्लिक कीजिए अरे इसके ऊपर क्लिक एक बार
Yeah, it's coming.
ये तो हेलो
Yeah.
हेलो हेलो
Yes, Dr. Mehta.
Oh, sir, my slide is visible.
No, your slide is not visible.
Hello,
Hello.
my slide is visible.
No, sir.
No.
I am sharing, but how it is not?
I think, sir, first you need to open your PowerPoint slides, then start sharing.
No, I have opened on my
Yeah, we can
desktop.
see. Now we
Now
can see your slides.
Now it is
Is
coming.
it
Yeah.
visible?
Yes,
Yeah.
it is visible. Now
So
please
should
go to
I start
slideshow.
now?
Yeah, sure. You start.
Please go to slideshow.
Okay.
Yeah,
Yes.
you can start.
Fine. Please start.
Okay. So my topic is good afternoon, everyone. I have slightly changed my topic. I have added some magnetic and electrochemical properties in my present talk. So the topic of my presentation is magnetic, electric, and electrochemical characterization of one double perovskite Zn-Mn06 ceramics for future applications. So this material is a functional material. So functional material can be designed by various approaches like crystallographic approach, metastable material approach, and by creating defects, and by hybrid materials. By designing hybrid materials, so we can create a, or we can design a new functional materials. So this is a, there are various examples of these functional materials under crystallographic approach, and this is these materials are examples, or these materials shows metastable state materials, and these examples are belongs to defect. By creating defects, we get functional properties of such materials, and there are so many hybrid materials which show functional properties, and these are actually the combinations of organic and inorganic materials to produce hybrid materials. So I am not going details for these materials. So let us I am starting. What are perovskite? So perovskite has a general chemical formula AbO3, and A is the corner site of the unit cell, and B at the center site, and oxygens lies on the center of each phase. So in this way, there is a octahedra, B06 type octahedra forms within the unit cell, and these octahedra are the B site atoms are under the cage of these octahedra, and for the same type of transition material which takes B position has the same size of octahedra, and the orientation tilting of these octahedra creates new functional properties of the perovskite materials. So in order to get the various properties, functional means the same phase can exhibit various properties like optical, magnetic, electrochemical, sensing property. So for this purpose, we have inserted one new magnetic or optical material at the B site of AbO3 perovskite. So in this way, we extend this simple perovskite. We can derive a double perovskite from a single AbO3 perovskite. So double perovskite now takes the form of A2B prime, B double prime O6, or we can say we can write this A prime, A double prime, B double prime, O6. So these double perovskite are designed to get the functional properties of our perovskite material. So double perovskites oxides are preferable compared to single perovskite oxides, because we have inserted the more than one transition metals, or more than one rare earth ions at A site. So in this way, we can achieve various functional properties for our futuristic applications. So we adopted double perovskite oxides for our technological applications to get perovskite material. So in this way, what is the difference between simple and double? In this way, there are the different type of octahedra forms in double perovskites. One is a B prime O6 type, another one B double prime O6 one. So these are our materials we have synthesized in our lab. So the diverse functionalities, there are various applications of these double perovskites oxides by forming the alternate arrangement of two types of octahedra, as in the case of rock salt structures. So double perovskite magnetites have various applications in magnetic, in sensing, in sensors, and multi-state memory, and spin tunneling junctions, solid state fuel cell electrolyte. So we have taken Mn as one of the constituent of this double perovskite oxide. So we why we took this, because it possesses half metallic ferromagnetic, high ferromagnetic Curie temperature. Tc can be raised by changing doping species, concentration, pressure, magnetic field. Magnetites prototype a strong electron correlated system, and a double perovskite in the form of double perovskite magnetites have new mechanism at origin of magnetoelectric properties. So we have adopted to characterize the electrical property. We have adopted impedance spectroscopy by using these various formulas, various electrical parameters like complex permittivity, complex electric modulus, complex impedance, and complex admittance. And these are correlated with these formulas. And using these formula, we have characterized that materials. And we have adopted electric modulus formula in this case, because it is just the inverse of the complex permittivity, which gives the complex electric modulus. So what is the advantage? Why we are choosing this formalism? Because in the bulk relaxation properties, the high values of permittivity and conductivity at low temperature are hidden in the permittivity presentation. So due to these reasons, due to the region of electrode nature and contact, space charge injection phenomena, absorb impurity conduction effects, our permittivity presentation are obscure. So to remove or to resolve or even ignore these difficulties, these three difficulties, we have adopted electric modulus formalism. So there are two types of dipolar relaxation here, dipolar relaxation mechanism and conductivity relaxation mechanism. So dipolar relaxation mechanism can be studied using this formula, which is given by device, call, division call, and Hurwitz Nigami equations. So using these various models, we can study the dielectric properties of the said materials. So in case of conductivity relaxation, we have used Johnson's formula. So in this case, AC-DC, the conductivity are connected in this way. So we can study the conductivity relaxation using Johnson's formula. And we can know the activation energy of our charge carriers. We have used these formulas. So there are various preparation methods of such type of materials. We can we can synthesize double perovskite materials by ceramic method, soft chemical methods, and other methods like interaction, disintegration, high pressure synthesis, vacuum, heat treatment, melt, and quench technique. And processing is done by inject printing, screen printing, and spin coating. So we have adopted a simple method here, solid state synthesize method. So these are our constituent ingredients, which are weighing in stoichiometric proportion and milled for 3 hours at room temperature, and mixing is done for a long time, 10 hours, and calcined at 1250 Kelvin. And in this stage, phase formation was checked by XRD, And by this flow chart, we finally get a dense lanthanum zinc MnO6, which is our present material, and characterization, various characterization is done. So these are the crystallography structure. These are the X-ray diffractogram, and this is the ritual refinement. So this straight line below this experimental and measured data, this flat lines indicates the good quality of fitting of these ritual refinement, and results are given in these tables. So in present case, the material get crystallized in orthorhombic PBNM or structures. And this Raman spectra also supports our XRD refinement. And there are various peaks of Raman spectra here. So this indicates the rotation or tilting of MnO6 octahedra. And we have checked the tolerance factor, whether this double perovskite oxide existed or not. So we found the tolerance factor 0.84 here. So 0.48 indicates the monoclinic or orthorhombic structure. So this also supports our refinements. And this is the ASEAN micrograph. So there are various grains of unequal size, and nearly spherical grains are observed. The grain size range on average is 2.25 micrometers. So these are the back scattered compositions of this ASEAN. So back at scattered image of the same material is shown in this figure. This is in figure D. This shows the agglomerated grains and some porosity with higher magnifications of this figure C. So this is the composition. ADS spectra also supports the our measure. This whitest area is the major phase of this material, which is the composition of all the constituents of the present material, and these defects or dark regions indicates the minor phase, which shows the lack of lanthanum. Lanthanum concentration is lacking in this dark region, in minor phase regions. So this composition in atomic weight percent is shown in this table. And dielectric property shows the conventional property shows, but with high dielectric constant. And in this case, dielectric load is higher. This is due to conductivity relaxation. And we can see here, there are some peaks. So these peaks show the relaxation process in the material. And these peaks go beyond our measured frequency range as we increase the temperatures. So we have adopted here the electric modulus. The same data can be presented in this form. So in this form, the modulus value increases with increase in frequency. So, and at low frequency, it reaches to 0, and at higher frequency, reaches to its asymptotic value. So this property indicates there is negligible contribution of electrode polarization in the modulus representation. And at the middle of this frequency range, we get the dispersion. So this indicates the conductivity relaxation here. So there are various peaks in complex part of electric modulus. This shows that the thermally activated nature of the material, because the peak shifts towards higher frequency range with increase in temperature. And from these peaks, we have calculated the activation energy here, which is 0.35 electron volt. And we have used various another model to fit the peaks. These peaks are
Dr.
fitted.
Mehto?
Yes, sir.
Actually, we are running short of time. If it is possible, within 5 minutes, if you can compile it.
Oh, okay. I'll conclude within 5 minutes.
Sure. Okay.
So this is various models of to confirm our modulus data, and this is AC conductivity, and the AC conductivity decreases with decrease in temperature, and shows the DC conductivity at lower frequency range. Okay, So, and from this DC conductivity, we have again calculated the activation energy. And here, this is the scaling behavior. So this shows the dynamic processes at various frequencies as temperature independent. And this is the resistivity of this material using Morse formula. And this is magnetic property. So in magnetic property, we have fitted using Curie's law. And this is the magnetization versus magnetic field. So very low value of coercivity and low value of remanent magnetization is observed in this case. And this is the sensing property, how this is used as a sensor. So we have purged different gases here. The sample is mounted in cold head of a closed cycle refrigerator, where in addition to temperature variation, the sample chamber may be purged by various gases at different concentration, or you can say pressure. After the gas is purged, the sample is left for a waiting period of 15 minutes before each measurement for homogenization of absorption. So here, with the increase in pressure, the semicircle radius is increases here. So with the help of this intercept on the x-axis, we have plotted the resistance versus pressure. So here we get different slopes. So these slopes show the sensitivity to the gas of these materials. So there are three gases, nitrogen, oxygen, argon. So here the slope is maximum for this nitrogen gas, and this is more sensitive than the other two gases, oxygen and argon. And this is the same plot at various temperature at the atmospheric pressure. So in this case, with the rise in the increase in temperature, the semicircle decreases. So the conductivity decreases with the increase in temperature. So semiconducting behavior is also observed here, and various activation energy are calculated from that plot. And this is cyclic voltammetry. So we our each cycle is increases with increasing scanning rate, which is volt per second. So this is a square type cycle with increasing in the area is increasing with the increasing scanning rate. So this indicates this is useful for electrochemical double layer capacitors and pulse power source in digital communication and electric vehicles. This property is this shape of the loop is very much useful. And this is charging discharging cycle with the increase in current density. Our time of charging discharging is decreases. So this is also useful in various applications. And general concluding remark is major challenge of new multifunctional materials. Their synthesis are going to play an important role. Rational design approach is used. The opportunity is the exciting properties. So acknowledgement to the organizers of this conference and my colleagues, students, and all collaborators. Thank you for your kind attention.
Thank you, Dr. Mato. It was really a very good talk. And since we are running short of time, so
yes, sir. Thank you.
Okay, so before I ask Professor B.K. Pandey, who is head of the Department of Physics and Material Science, Madan Mohan Malviya University of Technology, who is a co-chair of this particular technical session, I would like to thank Professor S.N. Tiwari, Dean Faculty of Science, Professor Shantanu Rastogi, Head Department of Physics, and Dr. Srivastav for giving me an opportunity to chair this technical session. It was really a very interesting talk, actually. So over to Dr. B.K. Pandey.
Sir, we will start the next technical session. That will be technical session 4 after 5 minutes. I've already informed Professor V.K. Pandey.
Okay.
He will be rejoining us within 5 minutes. So I will request all the participants and speakers to rejoin after 5 minutes. Thank you.
Okay, thank you.
Okay, thank you.